I'm Betsy Green, Executive Director of the Georgia Youth Science and Technology Centers. I am so happy to introduce you to our organization and the wonderful work we do. For 31 years, GYSTC has been the leading nonprofit advocate in Georgia for excellence in science, technology, engineering, and math education at the elementary level. We advocate for our hardworking Georgia teachers with ongoing professional development training so they can maintain the highest skill levels to prepare our children for success. We advocate continuously for quality science education for Georgia children and their families with year-round activities for kindergarten through 8th grade students. Our reach is statewide with special focus on those children and communities who are underserved and need us most. We are enthusiastic and we are creative. GYSTC programs are available so entire communities can come together around science-based exploration, education, and fun. Today, I'd like to share one such program we are most proud of, Georgia Discover Camp. As you will see, it's a learning camp with a science twist. Any Georgia student can participate and every Georgia student will enjoy what we have in store. Please take a look.
Good morning. Welcome to the last day of camp. We appreciate you taking your time this summer to participate with us in our Discover Georgia STEM Camp over the last 3 weeks. So, right now, I want you to sit back and relax and come with me on a trip to Providence Canyon. Good morning. Thank you so much for participating with us in camp this week. Today we have a real treat. We're here at Providence Canyon. In the backdrop you see Providence Canyon, and in just a few minutes we're going to take a trip down to the canyon floor, and Dr. Bert Carter, geologist from Georgia Southwestern, is going to share with you the knowledge of the formation of Providence Canyon. Get ready, get prepared. You're in for a treat. Thanks so much for participating with us this week.
Hello, my name is Bert Carter. I'm a professor of geology at Georgia Southwestern State University, and we're in Providence Canyons today. Not that you can see the canyon right now, but we're in Providence Canyons, and we're going to think about time. Whenever I start teaching an introductory class in geology, I like to ask the students, what is the definition of geology? And they always say it's the study of rocks, or it's the study of the earth, and that's okay as far as it goes. But really, geology, I tell them, is the study of time. We're not interested in the rocks as they are right now. We're interested in how the rocks got where they are. We're interested in not how the place looks now, but maybe how the place is going to look sometime in the future. So we're always interested in time when we think about geology. And there are 2 ways that we can go with it. When we think about present conditions and try to predict what eventually is going to happen in the future, we generally are doing that in service of what we call environmental geology. So when we're projecting into the future, we're always thinking about what the environment is going to be like. But we also like to project things into the past as well, and to think about how they got to be the way they are right now. And so this is a really good place to do this sort of basic thinking about geologic time. The idea that the Earth is a very, very old place dates from the late 1700s, and mostly the work of one person whose name was James Hutton. He lived in Scotland. He had a farm. He would notice that some of his farm was going down all the little gullies and rills and into the nearby streams and into the bigger streams, and eventually they were winding up in the North Sea. So his farm was going away, and he wanted to know what was going to happen when all of it was gone. So the whole idea of geologic time really is something that we can think about right here, because we're going to see lots and lots of things that make it clear that this place has been being eroded, like Hutton's farms, and that all of that stuff is going somewhere. So what I want to do is start with today, and then we'll work forward and we'll work backwards from those 2 things. We can see when we're in the canyon or when we're up at the top looking at the canyon, we can see that erosion has been going on in the past. So first thing I want to do is point out what is it that's going on today, and we'll think about that, and then we'll think about geologic time in both directions from there. So we're right in the bottom of the canyon, and there is here this really cool stream. This is called a braided stream, and we know that braided streams form when a stream is trying to carry more sediment than it can possibly carry. So you can see lots of little channels up through behind me, small channels. They divide and go around the sandbars, and then they come back together, and then they divide again. It's a very complex system of channels separated by these longitudinal bars. So the whole thing is dynamic, but the thing is constantly changing. But the one thing that it's always doing is moving some of this sediment. Okay, so you can see that the water going through the stream is not perfectly clear. Sediment, very, very fine sediment in it that's called suspended load, and that's what makes it murky. You can also see sand grains that are rolling or bouncing or moving along here. So even a stream this small is moving some of this sediment, but it doesn't have enough power to be moving that sediment, for example. You might be able to see that it's eroding into this side right here. This longitudinal bar is now being cut a little bit right under my feet. The water moves very, very slowly across slightly deeper bars, and so the sand is not moving as effectively there as it is in the channel. But all of this sand is going downstream. So if we think about the implications of this for the future, this sediment is all going down to the Chattahoochee River. And when it gets to the Chattahoochee River will carry it downstream again. And right now, almost all of the sediment, except for the suspended load, all of that sand that's rolling along the bottom here winds up near the head of the nearest lake that's dammed up on the Chattahoochee River. All of this sediment is going down toward Chattahoochee, toward Apalachicola, but most of it's not making it anymore. And if you do go down to the coast of Florida, you'll find that most of those islands are being eroded away. Cutting off this sediment at those dams is having a detrimental effect on the barrier islands down on the Florida coast. Some of them have receded dramatically, some of them it's not quite so obvious, but they're all sort of losing ground, if you will, because the sediment supply from here is being cut off. So if we think about where this sand should be going, then we can think about the environmental consequences of decisions that were made to put those dams in, for example. But I also want you to think about where this sand came from. If I get a handful of the sand out of this thing and look at it, I find that there are at least 3 kinds of minerals in here. So I can see some sparkly stuff, that's called muscovite. It's a kind of mica. But most of what's there is a mineral called quartz, and that's pretty common in sands. But there's a good bit of this muscovite mica, and then the reason that it's sort of pink or in some cases red, right? There's not very much really fine stuff in here, a little bit of clay, but not very much. It's almost all quartz, some muscovite mica, and a little bit of other things as well. And we're going to compare that in a little bit to the kind of sand that we see in the canyon. Right. This little stream originates in the canyon, and the only place it can be getting this sand is from the walls of the canyon. So this sediment is coming out of the canyon walls. Every time it rains, some of it gets washed down here into the bottom. So right now, this stream, and even the bigger stream that you're looking at, has a pretty good bit of sand in it. But if you think about how much sand has gone out of this canyon, right? If you think about the volume of sediment that is already gone from here, it's pretty tremendous. The area of the park is a little over 1,000 acres. I'm not sure what the proportion of that is canyon and how much of it's parking lot and all that sort of thing, but probably a few hundred acres. And the average depth of the canyons is probably 100 feet. So you can think about how much sediment that is. That's how much sediment has already gone down the Chattahoochee River and is down on the coast of Florida somewhere. So when we're thinking about geologic time, we can think about where this sand came from. That's not a big surprise. The source of the sand, we say, is the walls of the canyon. What James Hutton did that nobody had ever thought about before was to think the canyon itself is made out of sand, and all of that sand had to come from somewhere too. So where did that sand come from? It had to come from a place that had quartz and mica and some other things that we'll talk about when we get to the canyon wall, right? And the best source for those kinds of things would be an igneous rock or a metamorphic rock. The muscovite ultimately would come from some sort of a metamorphic rock like schist, or it might come from granite. The quartz could come from either of those places as well. So the rock in the canyon walls, right, is just as loose almost as this. This sediment came from those canyon walls, and I've said that those canyon walls, the sediment in those walls, came from an igneous or a metamorphic rock. Right, so what we need to think about is, where is the nearest place that we can find igneous and metamorphic rocks that might be the source for the rocks in the walls of Providence Canyon? And it's really pretty easy. It's not more than 10 miles away from here, in fact, that we get into what's called the Piedmont of Georgia. And the Piedmont of Georgia is made of metamorphic rocks and igneous rocks. Right? So the Piedmont of Georgia was the source for the sand in the walls of the canyon, which is called Providence sand, by the way. And the canyon walls are the source of this sand. And eventually this sand winds up in the Gulf of Mexico. And James Hutton would have pointed out there's no reason in the world that you couldn't eventually uplift that area, and that sand would then be the source for another sand that would be deposited somewhere else, and so on and so on. And where does it end? Okay, so we've moved up the canyon now, and if we look at the stream, we find that there's even less water here than there was farther downstream. The bars are much more obvious, the channels are much fewer and far between, right? But it's the same kind of stream. It's still a braided stream. It's still moving sediment, but up here it's not as effective at moving the sediment than it was even down there. We came up here so that you could see that wall in the back. Now you can look at the Providence sand, and you can get some idea of how much sand has gone out of this place since this canyon began eroding sometime in the 1800s. Remember, all of it's going down to the Gulf of Mexico. All of it came from somewhere else. And if we look in the valley walls here, we find pretty much the same thing that we find in the stream. Remember, that's no big surprise. There's a lot of quartz here. There is some of the muscovite mica. But there's something else too. This is not a single piece, it's a lot of pieces of quartz, and it's being held together by a lot of clay. There's a lot of clay in here. So now if we think a little bit farther back in time, all of that source area, right, that used to be rocks in the Appalachian Mountains, in the Blue Ridge and the Piedmont, is now in the coastal plain. So if we think backwards and take all of this material back up there and pile it back on top of the Blue Ridge and the Piedmont now, from Texas to Alabama, from Alabama to New Jersey, if we think about how big those mountains had to be, the Appalachians, when they first formed, were probably the biggest mountain chain the planet has ever seen. And now they're just little eroded stubs of what they used to be. And we know that for two reasons. We can think from what they had to be before to the coastal plain sediment that we see now. And we can think about how deeply the rocks that are exposed at the surface now had to be buried in order to be the kinds of rocks that they are. And those things tell us that there must have been tens of thousands of feet of mountain, where now the highest mountain in Georgia is not even a mile, not even 5,000 feet. That's what's left of it. But in eroding that away, it gave those of us who live in the coastal plain somewhere to live, somewhere to stand, somewhere to talk about this beautiful place.
I hope that you all enjoyed our trip to Providence Canyon. Dr. Carter talked a lot about how the canyon was formed and about sediments and deposits. So today we've put together an activity dealing with erosion and deposition. Dr. Tom is going to come up and he is going to show you all about soil and how it can be moved via wind and water, just like the soil at Providence Canyon is moved from one point to another.
Hi everyone. Hey, I'm Dr. Tom, and hey, we just saw an excellent video that showed the amazing erosion that's happening in Providence Canyon. And you know, we know that day after day, the rocks on the surface of the earth are being modified by wind and water and ice and chemicals. And those are very powerful forces that act on those rocks overall. And the process of actually breaking down those rocks into smaller pieces is called weathering. And that's a little bit confusing because it sounds like weather, but it's really a different process, and it's called weathering. And it turns out that there's two types of weathering. There's mechanical weathering, where the rocks are broken down by physical forces that act on the rocks. And then there's chemical weathering, where the rocks are actually broken down by chemical reactions. And one of the most powerful agents of mechanical weathering is actually water, and especially water when it freezes. And one of the really cool things about water, and one of the unusual things, is that when it freezes, it actually expands and takes up more space. It expands about 9% and takes up a lot more space. And as it does that, it actually pushes out on the rocks and it pushes them apart, as you can see by that slide there. So what happens is the water tends to seep into the cracks between the rocks a lot of times in the daytime when it's warmer, and then at night it gets cooler, the water freezes and the water expands and pushes on those rocks and breaks those rocks apart over time. And hopefully you can see that one rock there, and you can see that the impact of weathering over time on that rock, and you can see how broken and cracked apart it is. But I wanted to show you a couple examples that you can see for yourself. And one thing we're going to look at is an egg, because as it turns out, an egg is mostly water. It's about 80% water or so. And so this egg is just a raw egg. And I wanted to show you that, but I took another egg yesterday and I put it in the freezer. And so I froze all the water inside of that egg. And when I did that, that water is going to expand by 9% and push really hard on the surface of that egg. So let's take a look and see what the frozen egg looks like. So here it is. There's that frozen egg. But if you look and see what happened when that egg froze. It actually pushed really hard on that shell, and shells are really strong too, but it broke that shell and made that giant crack in that egg just overnight. So when water freezes, it can push really, really hard and exert a lot of force on objects, and even enough force to break apart rocks. And so one more cool example that I wanted to show you was actually this jar of water. And so this is a mason jar here, and you can see it's almost full of water, but not quite. And I took this mason jar just like it yesterday, and I put that in the freezer along with the egg. And I want you to predict, what do you think will happen to that jar now that the water has frozen inside? That's a pretty strong jar, and it's a pretty strong top on top of it. So let's take a look now and see what happened to the jar that was frozen. And I have it in a bag here. I'm gonna have to be a little careful getting it out. But if we take it out here, you can see that that jar has actually broken apart. And the force of that frozen water pushed so hard on that mason jar that it broke that mason jar into pieces. So the force of freezing water is really pretty amazing, and it's one of the most important agents of erosion that we have on the earth. So that's pretty cool overall. All right, now, mechanical weathering, guys, can also be modeled, and we're going to model it today doing some candy weathering, and hopefully you got a chance to get some candy. Skittles work good, M&Ms work good, gumballs work good, just kind of any kind of hard candy with a little bit of a coating works really good. I'm going to take a couple gumballs, and what I'm going to do is imitate weathering, and I'm going to imitate the motion of waves. And when waves hit on the shore, they actually push the rocks kind of back and forth like this, and that'll start the weathering process. And that weathering process over time, just like the freezing of water, can be really, really powerful. And I want to show this quick little video of these waves that are hitting the shore, and it'll give you some idea as to the power of those waves as they're crashing into the rocks on the shore of the ocean. So to me, that video really does a good job kind of showing the power of those waves. And here's a couple rocks, and so we couldn't see it really well, but as those waves hit, the rocks tend to crash into each other and bang into each other, and over time that starts to wear on those rocks. And you can take a guess and see which of these rocks do you think are more weathered. Do you think it's this one or this one? And you can kind of think about that and consider it overall. Okay, so now let's get back to our candy weathering again. So I want you to take 2 of your pieces of candy, and then I want you to try to model that process of physical weathering or mechanical weathering by hitting them against each other in kind of a wave motion over and over again. So let's go ahead. So I'm going to try to do that. I want you to kind of keep repeating that process and try hitting your rocks. And this occurs probably a little bit more slowly as the waves come in. But that's really the process that leads to weathering related to waves. And now I can look at that and I can see I have a little bit of weathering on the surface of my rocks. I'm going to try another kind of candy too. I have some Mykonikes here. And they're a little bit easier because they're a little bit softer, but the same kind of thing. So now Mykonikes are my candy rocks. And if I rub them against each other, like would happen in the surf and the waves, I can see that over time, the surface of those candy rocks starts to wear, and little pieces of it basically break away. So now if I take a look at that, I can see that the surface of those rocks are both kind of weathered. And I can see the small pieces of the sand that would break off. And there's a reason why in the ocean you don't see a lot of big rocks around, and it's because those big rocks are pulverized and pulverized and pulverized until they get to be really small grains of sand over time. Okay, now the second kind of weathering that we talked about is chemical weathering. And chemical weathering is where rocks are broken down by chemicals instead of by forces. And so for that, I want you to take another piece of your candy. Doesn't really matter which one. I'm going to take a green gumball in this case. And then I want you to expose that candy to some chemicals. Now, if you have some vinegar, I want you to use a little bit of vinegar. But if you don't have any vinegar, you can actually just use tap water, because tap water has chlorine in it, and it has fluoride in it, and it has other chemicals in it too. So regular tap water will work just fine too. So I have a little bit of vinegar here. I'm going to put my sponge in, collect a little bit of the vinegar. Then I just want to squeeze some of the vinegar out right onto my rock. In this case, my gumball. So I'm going to squeeze a shot in it, Squeeze another shot in it. Squeeze a shot. Then I'm just going to look really close for evidence of chemical weathering. Oh, and I can see some now. I don't know if you can see that on the camera, but I know at home you can see it while you're doing it. So some of the little particles of rock are wearing away and being carried away, in this case, by the vinegar, which is very, very similar to acid rain. So I can see, yep, this rock is chemically weathering and getting broken down. And over time, chemical weathering can have a major impact at really slowly kind of dissolving and eroding away rocks, even great big boulders. So I hope you got a chance to see that chemical weathering yourself. And that's a pretty neat example overall. Now, the next thing I want to do is actually my favorite, is I want us to model the process of erosion. And erosion is the process where, as something is getting broken down into smaller pieces, how does it actually move away from the rock? And the moving of those little particles away from the rock is called erosion. And we saw a great example of the little pieces of rocks that eroded from Providence Canyon down into the little creek down below. And so for that one, I want you to do this. I want you to take several pieces of your candy, any ones that you want. So I'm going to take a couple gumballs. I'm going to take a couple of my Mike and Ikes. I'm going to come here and grab a couple Skittles. And these are all going to serve as different kinds of rocks. So I have some smaller rocks and some bigger rocks. And I'm going to try to model the movement of those small pieces of rock from away from the rock to another spot. So then I'm going to just take a little bit of water, and water is going to serve as my agent of erosion. And I'm going to try to cover up the bottom of these candies with just a thin layer of water. So I'm going to go ahead and pour that in. Now I got a thin layer, and it doesn't matter a whole lot exactly how deep it is. And now I'm going to look for evidence of erosion. So I want to see, are these rocks starting to break down? And then are the little particles of rocks moving? Oh, and I can actually see they're actually moving already. You can see the particles from the blue rock moving away from the blue rock. And it's working really well on my red Skittles too. And normally the force for this would be provided by wave action like we saw, or it might be provided by the current in a river, or it might even be provided by wind whipping against the rock on a canyon wall or something like that. But I can see some beautiful erosion occurring right now in my candy rocks. And they're actually making kind of a cool pattern. Isn't that cool? And I hope it's turning out this well for you guys. And some of my colors are kind of coming together, and that might represent like different types of minerals actually mixing together. And so my sand would have different types of minerals as part of a mixture of that sand. So that is really, really cool. I'm so glad that worked well. Now, the one other thing I want us to try, if you have any candy left, and if you haven't eaten it all, is I want us to try putting some rocks in and then trying some wave action, and then you could try some wind action too if you want to. So if you can, I want you to get another plate that you can use, or you can dump out your first plate. That's okay too. But I'm going to get another plate in here, and I'm going to get some rocks again. I'll get a couple gumballs. They seem to work pretty good, and some Skittles. And I'm going to try to line them up a little bit this time. That might be impossible to do because my gumballs are rolling around. But I'm going to get a few different things here. We'll try a couple M&Ms this time. So this time I've kind of lined up the rocks like maybe they would be on the shore of a creek or a river or something. And then I'm going to pour some water in again, and then we're going to try to have some action from the wind and some action from the waves too. So you could do something like this, then go ahead and add your water again. And let's see if we can get some erosion to occur. And one of the things, guys, you should think about is how is this like real erosion and how is this different, right? Because this is a model and this is candy, they're not rocks. So one cool thing to kind of think about is how is it similar to natural erosion and how is it different? And kind of think about that and consider that. It helps us to kind of process things and make sure we're understanding them as we go. So now, I can see that erosion along the surface of my rocks again. And so I have little particles of rocks eroding out into the water. Now, I'm going to try to add a little bit of wave action. And so I want you to think about how could you add a little bit of wave action. And there's a lot of different ways to do it. I'm just going to take my pen and I'm going to bounce it up and down in the water a little bit and see if I add some wave action, will that change the erosion, maybe speed it up or slow it down or something? But I'm going to just try that and see what happens. And you can try that too. So if I try that, now I'm trying to get some wave action. And so stuff's moving around quite a bit. I just knocked one of my big boulders. But so by adding the wave action, it kind of changes the dynamics of the erosion a little bit. Maybe speeds it up a little bit, maybe mixes it a little bit more. But so I kind of like that because at least we're trying to imitate the action of waves and how those waves might actually affect our system that we're looking at. And the other thing you can do is you can also blow on it to kind of take a look at how wind might actually impact erosion and be a factor in that process. So if I go back to my original one and just kind of blow on it, I can kind of see what happens. When I blow on that surface. So I can consider that because we know that wind causes considerable erosion also. So anyway, so that's our model of candy erosion. And so we got a chance to look at mechanical weathering with candy, and then chemical weathering with candy, and then erosion with candy. And so I hope it worked well at your house today too. And I know you had a good time on the field trip to Providence Canyon this morning. And so we'll go back to Miss Lynn Larson, and we hope you had a great time with our summer school class today. And take care and see you soon.
We've had a great 3 weeks presenting materials to you and traveling across our great state. We hope that you've been exposed to some new things, that you've been able to see some new places, and that you are ready to go out and explore and be inspired to learn all about STEM. We appreciate all of the pictures that you've submitted to us. We appreciate all the dialogue that you've given us on Facebook, and we hope that you will continue to look to GYSTC for activities and fun things to do over the summer. At this time, we would like to hear a word from Mr. Don Barber, who is the State GYSTC Board Chair. Thank you again so much for participating with us this summer.
Hello, Georgia. I am Don Barber, Chairman of the Board of Georgia Youth Science and Technology Centers, Incorporated. I hope you enjoyed that short glimpse into the exciting world of GYSTC and the wonderful work we do. I would like to take a moment to say a few more words about exactly who we are and why our mission is so unique and so important. First, GYSTC is science-based and Georgia-focused. GYSTC is the only Georgia nonprofit advocating for excellence in science education for elementary school children and their teachers. Second, because Georgia is where we live, learn, and work, GYSTC is wholly invested in the growth and success of Georgia industry and its future workforce. The science education our children receive today will prepare them to meet the workforce needs of tomorrow in agriculture, manufacturing, forestry, cybersecurity, and so much more. GYSTC needs your help to ensure that we can continue the important work of preparing our youth for the science-based employment needs of tomorrow. Your monetary or in-kind contributions will enable us to offer Georgia kids more and better education. It will help us continue to offer our dedicated teachers more low-cost professional development training. At the corporate or individual level, every gift is important. Will you help us invest in Georgia's future? Please reach out to us. Every dollar invested is an investment in our children's future.